can see how the pMOS transistor transmit weak 0. That is, if we are trying to apply 0, then the output is VTP. So here it is a here we can see a pMOS transistor. The gate terminal of the pMOS transistor is grounded, so that transistor pMOS transistor turned on. And here a capacitor is connected, load capacitor is connected, that is shown here at the source CL. Then the drain terminal is also connected to ground. Here we can see that the VT, or the threshold voltage required to turn on this pMOS transistor, is minus 0.7 volt. And here VGS is also similar to VG minus VS. Here a low voltage is applied to the gate terminal. Ground voltage is applied to the gate terminal of this pMOS transistor, and as a result of this, the pMOS transistor turned on and the capacitor starts discharging. Okay, the capacitor starts discharging, and when it discharges discharges from VDD to 0, and when the value of the capacitor become minus 0.7, sorry, capacitor becomes 0, then VGS will be equal to VG minus 0.7. That is, the VG is the gate voltage, that is 0, and the capacitor starts discharging, and when it becomes minus it becomes 0.7, that is the threshold modulus value, minus VTP. We are taking the modulus value, then it becomes VTP. So VGS become VG minus VTP, that is 0 minus 0.7, then it becomes minus 0.7. That is the threshold voltage required to turn on the pMOS transistor. So the discharging of capacitor beyond 0.7 is not possible in this case, because if this capacitor discharge beyond this 0.7 value, then the VGS value become greater than our less than our threshold voltage, and as a result the pMOS transistor turn off and it will not work. So the discharging of this load capacitor CL is not possible beyond 0.7 volt. Hence we will get the output as 0.7, but we are trying to transmit a 0 through pMOS transistor. We will get the output only 0.7. That is the VTP, or it is a weak one. In NMOS transistor, the charging of the capacitor is not possible beyond 4.3 volt. In the case of pMOS transistor, the discharging of the capacitor is not possible beyond 0.7 volt. In both cases, if it charges or discharges beyond that value, the transistor turns off. So that is the reason why pMOS transistor transmit only weak 0, that is VTP. Here it is 0.7 volt. And that is the reason why we are also saying this pMOS transistor as a pull-up network, because it can transmit 1 safely. If VDD is the input, the output is VDD. And in the case of NMOS transistor, we are saying it as a pull-down device, because it can suitably transmit 0. That is, if 0 is the input, 0 is the output. But remember, NMOS transistor or N-type MOSFET is not capable of transmitting strong 1, and pMOS transistor or P-type MOSFET is not capable of transmitting strong 0. That is the principle. Now we can see how this transmission gauge connection works. Here in normal complementary metal oxide semiconductor CMOS technology, the input signals are only applied to the gate terminal, but here it is a pass transistor logic. The name implies it is passing some value from input to the output through transistor. So here it is N-type a pass transistor logic because n-type MOSFETs are only shown in this figure. The control signals for an n-type pass transistor, the control signals are applied to the gate terminal of the MOSFET. If we are using a pMOS, then also the control signals are applied to the gate terminal of the MOSFET, and the pass signals are applied to the source terminal of the n-type MOSFET. Here we can see this pass signals. Pass signals are applied to the source terminal of the MOSFET, and control signals are applied to the gate terminal of the MOSFET, and the product term, that is the output, it is coupled with the upper and the lower MOSFETs are coupled, so it is a product term, and that is the output we will get at the drain terminal of the MOSFET. So this is the basic structure of a pass transistor logic. Now we can see the features of this pass transistor logic. Here I mentioned all the advantages and disadvantages of this pass transistor logic in a combined fashion. First is that it is very efficient in use of transistors. That it uses only n-type for NMOS transistors for n-type PTL, and it uses only pMOS transistors for p-type PTL. And the number of transistors is very less, so it is very efficient in use of transistors. Then potentially very efficient layout result. Number of transistors are only one type, so the layout is also very easy to draw, and it is efficient also. Then pass transistors can usually be minimum size devices. That is, the area or W/L ratio of the transistors are very small, so the area also reduces. Usually more internal node capacitance than with conventional CMOS gates. When compared with the CMOS logic, these pass transistor logics have more internal node capacitance. Here we saw some capacitance already, gate to source capacitance, source to drain capacitance, like that. Internal node capacitance are more for pass transistor logic. Then propagation delay can become large in long series strings of pass transistors. If we connected pass transistor logics in long strings, then the delay will be a serious problem. Static power dissipation is unaffected. Dynamic power dissipation may be decreased. So when compared with CMOS logic, this static and dynamic power consumption are less. Static means leakage power, and dynamic means switching power. Both are reduced in the case of pass transistor logic. So these are the combined features of pass transistor logic. From that features, I separately wrote the advantages. It is very efficient in use of transistors, potentially very efficient layout results, then minimum size device, static power consumption is unaffected, decreased dynamic power consumption. These are the advantages of pass transistor logic. Now we can see the disadvantages. I already said there are some disadvantages for n-type and n-type and p-type pass transistor logic. That is basic working principle also. That is, the first is that NMOS device is effective at passing 0 but poor at passing logic 1. Only logic strong weak 1 will be transmitted to the output through an NMOS device. That is, if VDD is the input, that is, here we can see an n-type pass transistor logic, which the control signal is VDD, the pass signal is also VDD. That is, gate is connected to VDD, that is the control signal, source is connected to VDD, that is the pass signal, but at the drain terminal, that is the output terminal, we will get only VDD minus VTN. So the swing of the output is less, or the desired output is not obtained at the output terminal. And this problem becomes serious when we cascade more than one pass transistors, one n-type pass transistors. Here that is mentioned. Consider here two pass transistors are connected. N-type pass transistors are connected. In the node A, the input VDD is applied. In the node B means the control signal, that is also VDD, and then only this pass transistor turned on. The output at node X, that means output of the first pass transistor logic is VDD minus VTN, and it is again transmitted to another pass transistor logic, then the output become VDD minus 2 VTN. Then if it is there is another pass transistor, then it become VDD minus 3 VTN. So the cascading increases, the desired output value decreases, because if VDD is 5, then at node X it is 5 minus 0.7, that means 4.3. At node Y it is 5 minus 0.7 minus 0.7, that is 3.6. Then again it decreases if we increase the number of cascading. So this problem will be more serious if the number of cascading increases. And we also this problem we can also apply to pMOS transistors also, because p-type pass transistors are capable of transmitting only logic 1. In the case of pMOS, if it is a pMOS, here it is 0, here it is VTP, and here is also 0 gate terminal if it is a pMOS transistor. And cascading increases, it becomes VTP, then 2 VTP, then 3 VTP. When the number of stages increases, it also the value is also increases. So this is the main drawback of a pass transistor logic. And these are some of the reference texts that you can refer for further studies in the case of pass transistor logic. John P. Waimura's Introduction to VLSI Circuits and Systems, Sumo Kang's CMOS Digital Integrated Circuits and Analysis. These are the two reference texts which you can refer for the studies.